Okay, friends, let's start the next lecture. So, lectures 20, and from today we'll be starting discussing strong interactions. So, I put one because this will be a bunch of lectures, okay, which we'll be discussing over the course of next few lectures. Okay, so this is the starting point of understanding our review of meaning our review of strong interactions. So let's start with the basics to the begin with. So strong interactions, I think we covered earlier. There are two regimes of strong interactions. So strong interactions. What do you mean by regimes? Strong interactions. So these are regimes. So when you are probing subnuclear around, okay, one scale is regimes in scales means either in energy or in distances, because we're in relativistic theories. One is around nuclear scales, so other is much below the nuclear scales, much below the nuclear scales. So I will I'll try to distinguish these two what do you call the scales by putting a parameter, which will be clearer in the later half, essentially, when we are understanding by putting a parameter and introducing a parameter called lambda QCD. So uh, around nuclear scales and above is essentially when the typical energy scales are about, say, for example, lambda QCD, or in terms of the energies, in terms of the distance scales, it will be around Fermi scale. Okay, so this is say lambda QCD. The other thing would be, we will say, is much below 1 Fermi. So much below 1 Fermi. So the scales are extra, so subnuclear. Okay, so this is around 1 Fermi, and okay, let me just first explain it in terms of the distances. So this would be around 1 Fermi. So around the scales of around scales of the size of a nucleus, essentially. Okay, so what we have here is a typical nucleus which has a bunch of neutrons and protons. And so we will color the neutrons in blue and the protons in red, say, for example. Okay, so bunch of them here and there, and so the size of this thing would be typically several Fermis to Fermi. Okay, so when we try to understand physics at this scale, around say 10 power minus 15 meters, so we call this this is we try to understand the physics in a completely different regime in terms of neutron proton interactions. Okay, in terms of neutron proton, the stability of the nucleus and all these things, we try to understand everything in terms of neutron proton interactions. Now, if you try to go much below Fermi scales, so energy scales much below, there we end up having the quark structure and gluons as the mediators of the force. This regime is called QCD or perturbative QCD. So the entire thing is typically called as QCD sometimes. So, but this is has a name which is perturbative QCD. This theory, on the other hand, which is below um, around the lambda QCD and much below in energy scales, or around a Fermi in length scales and much above. In this kind of distances, we call that the theory is not completely well known. There are other. This is sort of a very strongly coupled theory, which is not explained as which we don't understand as well as we understand, say, perturbative regime of the QCD. Okay, this is some sort of a non-perturbative theory because the coupling constant is extremely large in this case. Okay, so this is not understood in terms of perturbative QCD. The coupling is not really perturbative. Okay, so how did we end up here within these two regions? In terms of the energies, this is distinguished in terms of something called lambda QCD. Lambda QCD is an energy scale Q square, say for example greater than equal to lambda QCD, which has a value about say between 1 to 2 GeV. Around this scale, when energy is essentially much larger than lambda QCD square, then the theory is described by perturbative QCD. And when Q square energy exchange is around or equal to lambda QCD, around or much below the lambda QCD, when the energy scale is so here you have several theories. The most popular of them is called chiral perturbation theory. Another thing which works very well, it is called lattice gauge theory. This theory is the non-perturbative regime of QCD. So this is the non-perturbative regime of QCD, whereas when energy scales are essentially much larger than lambda QCD, so around 1 to 2 GeV. So when the exchange particles carry energies which are above 1 to 2 Q to much above a GeV, perturbative QCD works. But also remember that uh, even though it is still technically perturbative, uh, the coupling is reasonably large, or even at that scale is around one tenth of a. Okay, it is not small actually. Even then it is around order one. Okay, it is just about order one, and even at 100 GeV square, it is about one tenth of one tenth essentially. The coupling constant is about one tenth, a bit more than one tenth. So it is. These coupling constants are not small. Okay, even though you call them a perturbative QCD, they are not as small as in quantum electrodynamics. So QCD is a challenging theory in both the regimes. Okay, in both the regimes, it's a challenging theory, but we can use the technology of Feynman diagrams and all these things in a much better sense, and loop expansion of the computation of the cross sections, and keep computing the higher order corrections in a much controlled fashion in the perturbative regime of QCD, even though the coupling constant is not small. Okay, that should be again, I stress this again. Even though we call it perturbative QCD, the coupling constant is not exactly small. It is reasonably large compared to say weak interactions or electromagnetic interactions. In the current perturbation regime, so at q square is going to much less than lambda QCD, around 1 GeV or something, or in terms of say the length scales, it is about a Fermi or a little bit below. It is definitely a non-perturbative coupling constant, and we have to develop different methods of understanding this thing. So today we'll start off with trying to understand. So the course of this next few lectures, we'll try to understand uh, uh, these ideas about uh, the strong interactions. Okay, and then both these regimes we'll try to study them. Okay, we try to study both these regimes, and then we'll see how far meaning and try to understand some intricacies about related to that actually. Okay, so let's try to understand a little bit about the origins of the strong interactions essentially. Okay, so soon after the discovery of the neutron and proton by Chadwick and everything, the question arose that how can, say for example, a nucleus can contain both a neutron, say for example, and a proton together. How is the nucleus binding? How is the nucleus binds together? Okay, both a proton and a neutron. I say, for example, if both of them are protons or a bunch of protons are there, okay, and a bunch of neutrons exist. So here I have three protons and two neutrons, say for example. So if we have a nucleus like this, the question arose that how this all these are binded together inside a nucleus. Now, why is this happening? Because protons are positively charged and neutrons are neutrally charged. So, whereas protons have electromagnetic interactions, okay, the neutrons do not have electromagnetic interactions. So, how is that? These particles are bound together inside a small region of space which is of the order of 1 Fermi, say for example, which is okay, small region of space which is of the order of 1 Fermi are confined to it. So this led to the ideas of having a new interaction which binds nucleons, the nucleons essentially neutrons and protons together inside a nucleus One obvious feature which is required by this new interaction is that it should be stronger than electromagnetic interaction. Further, um, it should not just be stronger than electromagnetic interaction, but it should also be short range. So what does it mean that it should? So the reason is that, as you know, that you cannot have a there is no strong interaction beyond the nucleus, right? Essentially, because the nucleons should be confined within the size of a nucleus, which is about 1 Fermi. So there is no way this range should be should be a short range interaction, so that the interaction confines these particles inside the size of a nucleus. So the first interaction which happened, which was proposed, was by Heidi Yukawa, who proposed something which is named after him. He proposed an interaction which is called the Yukawa interaction. So the Yukawa interaction, the basic idea here is that uh, uh, here you have an interaction which is stronger than the electromagnetic force, but it's short range. To make it short range, what Yukawa did was he observed that, suppose if you have um so the way he arrived at essentially is that if you have it's very similar to the electromagnetic interaction. Now the observation of Yukawa was that if you have the Poisson's equation, Poisson's equations for the electromagnetic interaction, so with some coupling constant, say for example G, this gives you a potential phi of r which goes as G by R. Okay. So this gives you a potential. Now, if you want to, now the point, if you want to modify this potential, now if you want to make, but this is this potential has a range which is infinite. Now the basic idea is that you want to make it finite range. Okay, so you want to make it finite range. So the way you go about doing that is introduce a mass. Okay, introduce a mass for phi. In that case, you can have delta square minus m square. Have to check all the signs essentially in terms of G delta cube of R. Okay, in this case, the potential phi of R would be e power minus mr G by 4 pi by R. Now, for a reason, so the range of this potential or the range of this force is set by the mass of the particle or the parameter m. Okay, so because there is an exponential separation sitting on the top, so this range will be of a finite range, it's no longer an infinite range, whereas in the case of the electromagnetic potential you have an infinite range. So the okay, now now so it's taking the range to be of the order of, okay, we know that by Compton effect, say for example about 1 Fermi. So we know the mass of the Compton radius of the particle to be so range to be 1 Fermi. So the Compton from the Compton radius, we know the mass of the particle should be around 100 MeV. So what Yukawa proposed was that, okay, there is a new interaction which is called the Yukawa interaction, which is an exchange of a scalar particle with mass around 100 MeV, okay, such that, so this mass is around 100 MeV, so that it is finite range with a coupling G, which is called the Yukawa coupling, okay, which is large, reasonably large, such that the nucleons are bound together inside the nucleus. Now for 100 m, so he proposed that there is a bunch of new particles, actually there are this bunch of new particles. So he proposed the existence of a bunch of new particles which are force carriers of strong interactions. So these new particles, the new scalar particles, he called were called pions. They were called pions. Okay. So these pions exchange. These are the exchange force carriers of strong nuclear forces. Just check the minus signs. I think there should be a minus sign here. Uh, Okay, check the minus signs. I was not very careful with the minus signs. Okay, okay. I think especially okay. So these are the force carriers of these pions are called the strong nuclear forces, and he said that they should be around 110, 100, around 100 MeV. Okay, and they should be detected. Eventually, the pions were discovered. Okay, we have seen the discovery of the pion and everything. Pions were discovered, and Yukawa got Nobel Prize. Okay, so there was some initial confusion. I think initially Yukawa called them as muonic forces, and there was some confusion whether uh, between the pion and muon actually for a long time. Okay, um, for a long time, and so but eventually they could distinguish pions and muons, and the main dominant decay mode of the pions is through the muons actually. Pi plus the charged pions essentially goes to pi plus going to mu plus mu mu. Now, the Yukawa theory is not a gauge theory. Essentially, there is no gauge symmetry involved. There is nothing actually. There is no symmetry argument to understand this particular interactions. Okay, it's not a gauge theory, so there is no symmetry argument. I'm sorry. Why? Okay, no symmetry argument to understand this interaction. Okay, so while this was a very nice uh, sort of an explanation of a theory. Okay, explanation for understanding the strong interactions. This was sort of not complete. Essentially, there was no people were not really happy. Furthermore, soon afterwards, when the pions were more understood, it turned out that pions experimentally when people understood pions much more better, it turned out that pions turned out to be pseudo scalars instead of scalars. So that means they violate parity. So they actually violate parity. Their decay modes actually violate parity maximally. We will see that in weak interactions because pions decay through weak interactions, and they ended up. So we could understand that they were actually pseudo scalars. Now, relativistically, you can understand pions or the scalar exchanges through. I'm sorry for this confusion coming from my iPad. Uh, some issue with my okay. Now, okay. Relativistically, uh, uh, the pions are understood in terms of the Klein-Gordon field, which we already saw. Are scalars and are thus described by the Klein-Gordon equation. In fact, you can actually write down the Lagrangian as follows. So if you have for the pions, so for a real scalar field, which gives you the Klein-Gordon wave equation, this is the equation of motion. This we have seen earlier already actually. We have studied that uh, we have studied the what do you call the solutions of this, which are essentially the plane waves. Okay, so e power I k of x so phi goes as e power minus I k of x or k mu x mu essentially. So we have studied the equations of motion and the solutions, the plane wave solutions, and so on. So now the point is that suppose if you have a source field essentially or a source term, this would modify the equations of motion. Say for example, if you have a source term del mu minus m square phi is equal to some source, which is some source which is a scalar source. And this source you can write it as rho is equal to some delta function source. So delta function x cube, okay, localized delta function source. Then you end up having if rho is not time dependent, you end up having as again the same equation which we started off earlier, as essentially a modification of the Poisson's equation, which is equal to g del cube of x bar. Now this you end up having a solution for this one if you do the Fourier transform and then do the integral, or the Fourier transform and the integral, you end up having the solution exactly the same way as what I have written here essentially earlier. This is exactly your Yukawa potential. So if you have a scalar field source, okay, the resultant potential will always be a Yukawa potential. So the exchange of a scalar field would be equivalent to having a Yukawa potential in the non-relativistic regime. Okay. So this is what is clear from us. So the Yukawa potential in the relativistic regime will just appear as an exchange of a scalar particle, and these scalar particles could be your pions. Okay, so this could be your pions essentially. So the simplest theory we can write down for a nuclear and proton theory, or let's just write uh, uh, a Yukawa theory in relativistic regime. In the relativistic case, so the Yukawa theory will appear. Let's assume the particle content of this theory would be consider two Dirac fermions, psi 1 and psi 2, and then a real scalar phi. So the Lagrangian would contain pieces which are essentially L Dirac 1 plus L Dirac 2 for the two fermions, L scalar for this, and then there will be some interaction term which we call it as a L interaction term. So let me write down these terms explicitly. So L Dirac 1 and Dirac 2 we have seen anyway, we have seen it as L del slash minus M or 2 psi 1 bar. Okay, let me y to let me write down even nicer. So L Dirac I is equal to psi I bar I del slash minus mi psi I, where I is equal to 1 2. Okay, each separately for the two Dirac fermions. Then for the scalar field, I have this the Klein-Gordon field essentially. It is the real scale. Let me write down for a real scale Klein-Gordon field. So del mu phi minus m square phi phi square. Now the interaction term is the Yukawa interaction term, which I write it down as y, or since we are using, okay, let me write it down as y because this will be useful for us later on, would be something like psi I bar or psi 1 bar psi 2 phi, because it's a complex Yukawa interaction. This would be a Hermitian conjugate essentially, because the coupling could be a constant. So this, in this case, what's happening is the phi is acting as a source field, okay, for the Yukawa interaction. So the phi is essentially acting like a source field. So this, if you do the non-relativistic regime, will give you the Yukawa potential between the two psis, psi 1 and psi 2 actually. So you can in principle write psi, make it more generic, psi I, psi j, psi I, psi j, where I need not be just I, you can have I j, meaning I could be the same thing. Say for example, you could have psi 1 phi, psi 1 psi 2 phi, psi, okay, and psi 2 to phi. So these are all the couplings you can in principle write. There is nothing stopping you. So there could be uh, several Yukawa couplings. One corresponding psi 1 1 psi I is equal to j is equal to 1, or I is equal to j is equal to 2. The other one is I is equal to 1 and j is equal to 2, and the other one is I is equal to 2 and j is equal to 1. So all these Yukawa couplings are possible, okay, and they all lead to the same interaction potential in the weak scale, the non-relativistic regime, which is essentially given by this Yukawa potential. And whose range is set up by the mass of the particle. Okay, again, whose range is set up by this mass term sitting here. Okay. Now, how do you write the Feynman diagrams for this one? The Yukawa interaction is represented by this, because the scalar field is always a dotted line. Okay, and phi, the two scalars. Okay, so now the arrows you have to be careful, because as of now we have not put any charges or any other thing on this particular case. So meaning in this particular toy model we have not put any charges or electric charge or anything. Uh, but one can instead use what is something called the chirality. Okay, we have not the curve interaction, because it's like a psi bar psi mass term. If you write in terms of the chirality, this will have the psi, this interaction term would actually, if you expand it here, this just becomes yij psi l r by psi r j phi plus st. So essentially, if phi becomes a constant, okay, this gives you the mass terms, which we will see later on actually. Okay. Okay. So as of now, let's not worry about the arrows, but this is typically the Yukawa interaction. So an exchange of, so if we are scattering by the Yukawa interaction, say for example of two nucleons, would be having Feynman diagrams of this particular type. So suppose if psi is essentially the uh, proton, so let's try to see what could be the particular types of particles which you can, exchanges we can have. Say for example, if you have neutron, so I'm not putting any arrow, but let's just say this is neutron, it can exchange a pi 0 to a proton. On the other hand, you can have another interaction between a neutron and a proton. A neutron and a proton can exchange a pi plus, say for example, uh, pi plus a neutron, this is a proton. Okay, so these are the exchanges, or these are the Feynman diagrams which are possible for say neutron proton scattering, because okay, because of the Yukawa interactions. So so for example, you can draw these Feynman diagrams and compute the neutron proton scattering essentially. So Feynman diagrams. So now I jumped a big jump. So okay, so what I did, I made a huge jump here. So what I did here was, I said that I started with a toy model containing two fermions, so two Dirac fermions, so psi 1 and psi I, and then I had a separate scalar which I wrote down by a Klein-Gordon field essentially, and then I introduced Klein-Gordon Lagrangian. Then I introduced uh, uh, Then I introduced an interaction between the fermions and the scalar by a term which is directly multiplying the two fermion fields with a scalar field essentially. So, and in doing so, I said that the scalar fields has a source. Okay, so essentially the fermionic scalar current acts as a source for the scalar field. So psi bar psi transforms like a scalar current, right? It's a scalar current. Okay, if you remember your bilinear invariance, the psi bar psi transforms like a scalar current, so it acts like a source to the scalar field. So together they form an invariant Lagrangian invariant part for the interaction term. So this is the interaction term, and this is how the scalars and the fermions interact with each other. I have not introduced any symmetry. I have not introduced uh, anything else. Okay, at this particular point, I just said this is a toy model, and then I drew the possible Feynman diagrams. So this I call it as the interaction vertex, which is IY. Okay, and then I started drawing psi 1, psi 1, psi 2, psi 2, scattering Feynman diagrams. So I started drawing the scattering Feynman diagrams for psi 1, psi 1 and psi 2, psi 2. So you can do the same thing for also for the other ones essentially. Now, then I completely jumped into the case where I introduced psi 1 to be the neutrons and psi 2 to be the protons. I made a huge jump by introducing from this toy model. I actually moved to the case where let me consider psi to be the neutrons and psi 2 to be the protons actually. So in the first case, I considered neutron neutron. So when I did this jump, I realized that one major thing that, say for example, if I consider neutron neutron to proton proton scattering, I need one particular type of pion exchange, which is like pi 0 exchange. Okay, which could be a pi 0. So this is pion, okay, is not charged, it's neutral. It could be explained by a real scalar field, which is exactly like the one which we have seen so far. Now if you have the so this is like neutron neutron going into a neutron proton proton. Okay, there could be another diagram in which proton goes to a neutron and a neutron goes to a proton. So where there is an exchange of neutron to proton. Okay, in this case I cannot use a pi 0, but I have to use a charged pion. Say for example, the exchange particle would be a charged pion, so this would be a pi plus. Okay, so this would be required that I introduce into the Lagrangian a charge scalar, because a neutral scalar doesn't carry any electric charge. So the pions I introduced in the toy model so far are completely neutral. Okay, they can only explain the pi 0 exchanges, say for example the kind of diagrams which you have seen here. But to introduce pi pluses, I need to introduce a charged pion essentially. So to introduce uh, and say for example exchange of n to p and p to n, I need to introduce, one needs to introduce charged pions are essentially a charged scalar particle. Okay, so this charged scalar particle is nothing but your pi plus pi minus. So you have three things: pi plus pi minus and pi 0. So there are three particles, all scalars, almost same masses, which can explain all the neutron proton scatterings essentially. So you can have now similarly you can draw other Feynman diagrams, like for example pion neutron pion exchange diagrams. You can also have the other say for example with pi minus you can also draw the other diagrams actually. Okay, so this no, we had draw. Okay, so this is the first uh, shot at understanding strong interactions by exchange or strong nuclear forces by the exchange of scalar particles which are both neutral and scalar. But as of now we have not encountered any symmetry as such, but the hints of asymmetry were existing long ago actually. They were there for a very long time. So let's look at the hints of asymmetry. One of the first symmetries of the understanding of strong interactions came from Heisenberg. So So what he observed was, if you look at the mass difference between neutron and proton, this is much below 0.1%. Actually, it's much below 0.1%. It's 1 by 1000 or something like that. So one mass of the proton is around 931 and mass of the neutron is around 939. So it is a zero point 0.8 by 931. So it's around less than 0.1%. So in principle, neutrons and protons can have, they could be degenerate. In principle, they have a symmetry can be considered as degenerate. Now, if they are degenerate for up to a small correction, so up to a small correction they can be considered as degenerate. So if they are degenerate, a new symmetry can exist in the theory. Now, how do I see that? So let's consider uh, uh, two fermions, Dirac fermions. Okay, so let's consider the same d1 di. Say for example, two Dirac fermions in the Lagrangian. So L di is equal to I del slash minus mi psi I bar psi I. Assume, so I is equal to 1 to 2. Okay, there are two Dirac fermions. So, okay, each of them is equal to, meaning has a mass m1, mi. So there are two, then their Lagrangians are given as follows essentially. Now assume that m1 is equal to m2, say for example. Okay, so let me write down the explicitly the Lagrangian now. This is psi bar I del slash. Okay, let me write down the mass term separately. Okay, psi 1 plus psi 2 bar I del slash psi 2, then minus m psi 1 bar psi 1 plus psi 2 bar psi 2. Because the masses are degenerate, so the mass term is the same for psi 1 and psi 2. Okay. Now what we can show is that this Lagrangian has an additional symmetry which is an SU2 symmetry. We studied SU2, right? Okay, so far we have studied SU2s and everything. So suppose there is a new let me representation. There is a representation, fundamental. Okay, let me call this to. There is a. So how do I show that there is a new symmetry? Now we have seen. Okay, let me. No, this is not the way. Let me just. Suppose there is a fundamental under SU2. There is a fundamental representation under SU2, which I call it as capital psi. And this psi contains the two Dirac fermions, psi 1 and psi 2. These are the two Dirac fermions. Okay. In that case, I can write down this entire Dirac Lagrangian, okay, of the two fermions as I psi bar del slash psi, okay, minus m psi bar psi. So this Lagrangian is SU2 invariant. The Lagrangian is SU2. This is global symmetry, of course. Okay. Okay. Now, so the point is that if I can club psi 1 and psi 2 and put it together into some sort of an SU2 fundamental, then I can write the kinetic term. So kinetic term is exactly is invariant. So the kinetic term is invariant under SU2 because psi 1 and psi 2. So there is I dash slash and I dash slash. So if I exchange psi 1 and psi 2, nothing will change. Okay, the masses are the only things which distinguish psi 1 and psi 2. Now if I exchange, now because the masses are all degenerate, okay, so I end up having degenerate an additional symmetry, which is an I can write down like this essentially. So if I expand this, now you can do the expansion and you end up having the same Lagrangian as before. So you'll get back the same Lagrangian as written here if I expand this particular Lagrangian. Say for example, if I expanding this will give you back, so this Lagrangian, so 1 gives you back 1 actually. Okay, so this Lagrangian is SU2 global invariant. So that means to start with, if we have assumed psi1 and psi2 are to be degenerate, you end up having a new symmetry which is an SU2 symmetry. Now this symmetry Heisenberg called it as the isospin symmetry. So now any calculation if you do, so the basic idea is that if you have a isospin symmetry, the neutrons and protons are degenerate and the corresponding symmetry is essentially the isospin symmetry, and you can do calculations assuming that there is exact isospin symmetry, but all the calculations will be subject to corrections which are essentially proportional to the isospin breaking effects, which are given by this small parameter, which let me call it as epsilon. All the calculations can be done assuming exact isospin symmetry subject to corrections of the order of epsilon. Epsilon essentially is the isospin breaking effects, which is as the mass difference between neutron and proton. So if this is the isospin symmetry of the neutron and the proton, how do the pions transform under the isospin symmetry? Because we need to know what the pions are. So neutrons and protons transform as fundamental. Okay, there is a fundamental means that is a spin half. So this is essentially J is equal to half representation, okay, of SU2. This is the J is equal to half representation of SU2. Okay, then how does the pions transform under SU2? Because the isospin is an exact sort of a very good approximate symmetry. If the pions have to meaning if the pions have to what do you call interact with them, okay, and then they should also transform, and because the entire Lagrangian should be roughly approximately equivalent to the invariant under the isospin symmetry. So this pions, so for example, in this particular case where you have pion interactions with the neutron and proton system, the pions also have to transform under the isospin symmetry. So how do the pions transform under the isospin symmetry? The pions transform as a triplet, or J is equal to 1 representation of SU2. So the pi plus pi so the pi plus pi 0 pi minus form a triplet of isospin. So you have the neutron proton forming a doublet and the pions forming a triplet under isospin actually. So with this you can understand how the um, uh, pions also transform. All the three pions are roughly essentially have the same mass except by a difference of the electromagnetic factor essentially. So now we look at how the neutron proton system interacts with the pion system. So because we had drawn already these Feynman diagrams saying that okay there exists this pi plus and pi minus and pi 0. Now we see that there is some symmetry argument now because there is an SU2 which is the isospin symmetry which seems to be determining these interactions essentially. Let's just see how this things will come. Okay, the neutron proton isospin system. So the way we can write down, so let's introduce. So this is j is equal to half. This is m is equal to plus minus half. So let the proton have m is equal to plus half, and the neutron would have m is equal to minus half. So okay, this is essentially the system. Okay, this is the m values of the m values just to represent ourselves. So this form an iso doublet of this type. This is also called, this is essentially the fundamental uh, of the SU2 symmetry essentially. Now what we can do is because the pions transform as a triplet, we need to form. So if we have okay, uh, we need to form an isotriplet here. Now because it's a doublet, the addition of two doublets, it's exactly like spin. No, essentially this exactly two doublets or spin half particles could lead you to something is a singlet, isosinglet, or isotriplet. Okay, so let's look at the isosinglet state. The isosinglet state of the neutron proton system would be so essentially 0 0. The spin of the state would be 0 0 1 by root 2. This will be p n minus np. Okay, the isotriplet state would be, say for example, this is the isosinglet state. So 1 1 would be just pp. 1 0 would be pn plus np, and 1 minus 1 would be nn state. Now the question is, now sorry, I said singlet. Now, do we know in nature a neutron proton system? A single neutron and a single proton system in nature is a deuteron. Okay, the deuteron is a state which has a single neutron and a proton. Now, whether the deuteron exists as an isosinglet or an isotriplet. Now, the question is the deuteron isosinglet or isotriplet? Turns out it is a isosinglet, because if it is an isotriplet, we should have seen pp bound states and nn bound states of very same magnitude essentially. So these states are not found actually. So we don't really have, say for example, these states which are found in the neutron bond states, no neutron bond states. Proton bond states of comparable energy found in nature. So that's the reason. So so it's essentially the deuteron is a isosinglet state. Now, but then using this technology we have, so we can actually start calculating various cross sections essentially. You can actually calculate pp going to deuteron plus pi plus p going, say for example, so several processes you can have pp going to a deuteron plus pi plus, so involving deuterons, isn't it? Proton plus neutron going to deuteron plus pi 0. So various states you can consider, with also deuterons in the final states essentially. And the corrections to these cross sections essentially would be always be proportional to the isospin breaking effects essentially. Then there are this pion proton scatterings and so on, so which one can compute. Okay, there also quite a few calculations one can do actually. Now, while the neutron nuclear forces, okay, so these all these possibilities are, meaning you can actually compute further. So this is Now this is this is the theory about isospin theory and the computation of proton neutron cross sections and proton neutron proton pion and proton neutron cross sections essentially. But to understand the nuclear forces, okay, we had just an exchange of a pion. Okay, we just looked at the exchange of pions. Okay, coming back to the nuclear forces, coming back to, so we realized that uh, first of all, the pion turned out to be some sort of a pseudo scalar and everything. So people were started looking at trying to explain the data using single pion exchange. So many models were started being built to understand, say for example, the strong interactions by exchanging a single pion. Say for example, because it's okay, the bound states and the nuclear forces and everything with a single pion. Well, that was not sufficient essentially, so they started exchanging uh, the higher and higher pseudoscalars essentially. So they started exchanging, say for example, say um, not just the spin zero particles. Okay, they started exchanging other particles, like for example beyond. So the people were started exchanging something called the beyond the pion exchange. So exchange all other mesons below the nucleon mass range, nucleon mass. So essentially up to 1 GeV. So up to 1 GeV, you want to exchange all other nuclear, what do you call, all other mesons which were existing. Like for example, the vector mesons like the rho and the omega were also being exchanged to understand the strong interactions essentially. Strong interactions. Okay, but to before that we had to understand that there was a so there was a proliferation of various kinds of mesons. Okay, there was a say for example, there was a pi, there was the eta, there was the sigma, there was the rho, there was the omega, there was the a0, a proliferation of the mesons. They're both vector type and also scalar, bosonic, and okay, bosonic particles essentially. So this led to some sort of a complete chaos, because you have huge number of mesons which we don't really understand, and there is no classification of these mesons and all this kind of business essentially. So in the next class, we will try to understand the classification of mesons first, and then try to come back to understand the strong interactions again. Okay, in terms of some other theory at the in this regime, which we call it as the chiral perturbation theory. So okay, so okay. So today, what we understood, just to summarize what we understood today we had sort of a lot of things which we understood. Meaning there was a lot of information which I have given. essentially that the strong interactions are understood differently in two regimes. One is the non-perturbative regime, which is around the scales of 1 Fermi and above, okay, and much below 1 Fermi. So there it is sort of the perturbative regime. In the energy scale, this is roughly said to be something called the lambda QCD in the energy scale, which is around a value of around 1 to 2 GeV, where we believe that we understand that the coupling constant is non-perturbative. So you need to assume some other theories other than just the perturbative theory of QCD. So below, but energy scales beyond lambda QCD, you use something called perturbative QCD, and at energy scales below lambda QCD, you use something else. We use something called the chiral perturbation theory and lattice gauge theory. So today we started off by looking at the non-perturbative regime. So trying to understand what's happening in the non-perturbative regime, and today we look focused on one particular understanding in terms of something called the Yukawa interactions. So the Yukawa interactions are essentially interactions between scalar interactions between the nucleons inside a nucleus. So the neutron-proton system, which interacts with a bunch of particles, with scalar particles, with a finite range, and the finite range is set by the mass of the scalar particles. Okay, finite range is set by the mass of this scalar particle, and these scalar particles end up being called as the pions, which have the masses of around 100 MeV, because that is the range of the force, which is around 1 Fermi. Corresponding to 1 Fermi, you have the Compton wavelength of a mass of a particle of a mass around 100 MeV. And this exchange of the scalar particle is what in the relativistic regime you can write it in terms of, say, for example, between Dirac fermions and a Klein-Gordon field. Okay, here I took the example of a Klein-Gordon field which is real, and then said that the scalar current, which is psi bar psi phi, psi bar psi, acts like a source for this the scalar field, and that ends up giving you the Yukawa potential at in the non-relativistic regime. So the interaction term in the relativistic part is essentially just psi bar psi times phi, which is the scalar exchange. So the scalar mediator of the force of the Yukawa force. The Yukawa force is mediated by this scalar particle with a particular mass, which sets the range of this force. So in that case, we can draw this kind of Feynman diagrams in the tau model. We have drawn these Feynman diagrams where the exchange particle is given, the scalar particle is just given by this dotted line. So then we went to the case of the, so suppose if you take these two Dirac fermions to be the neutron-proton system, we realized that we showed that if you should have at least three kinds of pions, because if you have a neutron proton exchange uh, uh, through a scalar, that scalar should be charged, whereas if they are not exchanged, that scalar is just a neutral scalar. But if there is an exchange particle, if a neutron and a proton are exchanged to each other, then that uh, uh, the scalar mediator would be a charge scalar, and so that could be a different kind of a particle, which could be a pion, a charged pion. So there are three kinds of pions now. There is a neutral scalar pion and two charged pions, which are pi plus pi minus. So now the question is, are there any, because the Yukawa interaction so far we didn't really have some sort of any hints of any interaction, meaning symmetry or anything. So we looked at the possible origins of this, any symmetry arguments for this, and the symmetry arguments we looked at are essentially the Heisenberg's isospin symmetry. The Heisenberg uncertainty, Heisenberg isospin symmetry stems from the fact that the neutron and proton mass ratio is very close to each other, and So that means that you can essentially take them to be degenerate and compute the corrections in terms of the isospin breaking effects essentially. So we showed then that if you have two Dirac fermions which are degenerate, there is a new symmetry in the theory which is called the SU2 symmetry, and this symmetry is nothing but the isospin symmetry. Then we showed that you can this under this symmetry the pions transform as a triplet, pi plus, pi 0, pi minus. Okay, they transform as an isospin triplet, and we showed then we so the way they interact with is when the pi so if it is a triplet, the pions transform as a triplet, and then the neutron proton system can exist either as a triplet or an isosinglet, or an isosinglet. In the isosinglet case, it turns out to be the deuteron exists as an isotringlet state, and in the isotriplet state, you have this kind of combinations essentially. This is what I have seen. We have seen essentially. So the deuteron which exists as an isosinglet state, and then we can compute the various cross. In principle, using the theory, we can compute the various cross sections, which are proton proton going to deuteron plus pion and so on. So whereas the pions exist as an isotriplets, the deuteron exists as an isosinglet. So the okay. Now finally we noted with that coming back to the system of nuclear forces, the single pion exchange was not sufficient, so people started looking at exchange of other mesons, like for example, which are all below the mass of the nucleons, like for example 1 GeV, which is the mass of the proton or neutron, roughly as a part of the. So there are several such mesons which were discovered in nature, like pions, eta, sigma, rho, omega, a0. So all these exchanges were done, and people were trying to understand the nuclear forces in this kind of by the exchange of these particular. All of them didn't lead to some satisfactory results. Okay, but going back to coming back to the question of the existence of these various kinds of mesons, so one needed some sort of a classification of all these kind of mesons. So what we will do next is the classification of mesons, and then come back to this questions about how to understand strong interactions and this non-perturbative regime. So I'll stop this lecture here actually. Okay. Okay. Thank you.